Welcome back to Part 12 of our technical training series on reliability engineering and risk assessment. Up to this point, we have successfully transformed our qualitative logic structure for the reactor vessel into a fully quantified baseline safety model. In our last section, we executed the calculation engine for a standard one-year operational profile. More importantly, we utilized the toolkit's cut-set view to audit the structural integrity of our design. We discovered that our system results in 11 minimal cut sets, each with an order of 3. This confirmed that our engineering defense in depth is operating exactly as intended, successfully avoiding any catastrophic single points of failure. While our baseline results look promising, real-world engineering systems rarely operate in complete isolation. Up until now, we have treated our overlapping layers of protection, the automated sensors, the electronic controllers, and the manual human pathways, as entirely independent entities. However, complex systems frequently share common support utilities, such as electrical power, cooling water, or pneumatic air. If a single support system provides utility to multiple independent safeguards, it creates a hidden vulnerability known as a shared dependency or a common cause failure path. If that shared utility fails, it can simultaneously disable multiple layers of defense at once, completely defeating the mathematical benefit of our redundancy. In this session, we are going to expose our model to this exact real-world scenario. If you recall from Part 9, we intentionally left our external power supply grid from our fault tree model. We did this precisely so we could study how changing our electrical configurations directly impacts our risk profile. Now, let us step back into the item toolkit interface to study the different scenarios. To evaluate the impact of this shared dependency, we will analyze our first electrical configuration, which we will call Scenario 1. In this configuration, we assume that the external power grid provides operational power to both our automated electronic safety lines and their respective electronic controllers. If the grid experiences an outage, it will simultaneously disable the electronic valves and prevent the controllers from issuing a command. To map this behavior into our existing logic structure, let's first locate the gate that represents the failure of electronic emergency valve 1. We will navigate to our project workspace and open the subpage for input stream 1. Here, we find the gate labeled GV1, which governs the failure of electronic valve 1 to close. Currently, this gate is structured as an OR gate, taking inputs from the physical-mechanical fault of the valve and the primary electronic controller. Because a loss of power is an independent, alternative pathway that will also prevent the valve from closing, the underlying logical relationship remains in OR relationship. We will simply add a new basic event beneath GV1, name it grid, and assign our predefined grid failure model to it from the library. Now that we have modeled the power dependency under our first input stream, we must replicate this exact relationship for our second automated line. Let's navigate over to the Input Stream 2 canvas page and locate gate GV2, which represents electronic valve 2 failing to close. Because both valves pull from the exact same physical power infrastructure, we must not create a brand new, independent event. Doing so would mistakenly treat them as 2 separate power grids that could fail independently, completely breaking the mathematical reality of our shared dependency. Instead, we will leverage the toolkit's replication features. Let's return to our first page. Right-click the newly created grid event and select Copy. Next, we will return to gate GV2, right-click, and select Paste Repeat. This repeat instance tells the calculation engine that these 2 nodes are bound to the exact same basic event. Any failure state that hits the grid will now instantaneously propagate through both automated safeguard valve lines simultaneously. Our mapping of Scenario 1 isn't quite complete. The power grid doesn't just actuate the physical valves, it also powers the electronic controller backend. Let's locate the G-control gate, which represents the electronic controller failing to issue a close command. Because a loss of power will directly cause a command failure, the power grid represents an alternative root cause for this gate as well. We will right-click our existing grid event once more, navigate to the G-control gate, and select Paste Repeat. Remember, as we established when building our qualitative branches in Part 7, G-control is already a shared transfer gate utilized across both input stream 1 and input stream 2. Because the gate itself is a repeat instance, you only need to paste the grid event under it in one place. The software will automatically update the controller logic across the entire model. With our shared power dependencies fully linked, let's run our updated model through the calculation engine. Click the Go button on the main toolbar to re-quantify the system, and let's open up the cut set view to examine the results. Immediately, you will notice a significant change. The number of minimal cut sets has increased from our baseline of 11 up to 15. Why did this happen? By introducing the grid variable across our automated safeguards, we have created a common cause failure path. Our initial, highly robust redundancy between electronic valve 1 and electronic valve 2 has been compromised. The shared power dependency generates entirely new combinations and pathways for the automated system to fail. However, notice that this structural change has not impacted our human protection layer or our mechanical relief valves, which remain completely independent of the electrical grid. Now let's consider scenario 2, where the external power grid is a shared dependency that also provides operational power to our emergency alarm system. To model this, we need to navigate to our tree structure and find the gate labeled G-alarm, which represents the operator failing to receive the alarm signal. We will right-click our existing grid event once more, select the G-alarm gate, and select Paste Repeat. If we look closely at the underlying logic, the operator can fail to receive a warning if the physical alarm unit suffers an internal failure, if the transmission signal path fails, or if the power grid goes down entirely. Because the loss of power represents an independent, alternative pathway to disable the alarm, the logical relationship for G-alarm remains in OR gate. Furthermore, because this G-alarm gate is a shared transfer instance utilized across both input stream branches, you only need to paste the grid event here in one place to update the logic across the entire system model. With our second electrical configuration mapped, let's run the quantification engine again by clicking the Go button on the toolbar. When we open the results summary to check our updated data, you will notice a fascinating structural shift. The total number of minimal cut sets has actually decreased to 12, but one of these cut sets now has an order of 2. This mathematical result indicates a major safety vulnerability. By expanding the power grid's footprint to include the alarm system, a failure of the grid now simultaneously compromises both our automated electronic protection and our human protection layers at the exact same time. Because a single power failure knocks out both lines of defense, the Boolean calculation engine simplifies the pathways, collapsing what used to be a 3-event scenario down to a more vulnerable 2-event chain. In this specific case study, the underlying failure rate of our power grid is low enough that it does not dramatically inflate our final top-level unavailability score. However, this shift clearly demonstrates the risk impact of different system designs, showing exactly how the item toolkit allows engineers to uncover hidden common cause vulnerabilities before a design is finalized. To summarize what we have accomplished in this session, we have successfully moved beyond our idealized baseline model to evaluate how real-world dependencies impact system safety. By utilizing the item toolkit's replication features, we analyzed 2 distinct common cause configurations. In scenario 1, we linked the external power grid to our electronic automated valves and their controllers. This introduced a shared dependency across our primary automated lines, increasing our minimal cut sets from 11 to 15. In scenario 2, we extended that same power grid dependency to include the operator's emergency alarm system. This structural shift collapsed our defense in depth, reducing the total number of cut sets to 12, but introducing a highly critical cut set with an order of 2, proving that a single grid failure could simultaneously compromise both our automated and human protection layers. While the low baseline failure rate of our grid kept the final top-level unavailability from skyrocketing in these specific examples, the structural vulnerabilities we uncovered are a stark reminder of why dependency modeling is so critical. Now that we have seen how shared variables alter the qualitative and quantitative paths of our fault tree, we are ready to close out our evaluation of the calculation results. In our next chapter, we will step away from the software canvas and return to our theory discussion to explore the other major piece of our risk assessment puzzle: importance measures. We will look at how reliability engineering mathematics allows us to precisely rank individual components to see which ones are truly driving our system risk. Thank you for watching, and I will see you in part 13.